Hello, I'm Joshua Freedman, Senior Analyst at Rapaport, and welcome to the second episode of Rapaport's new LinkedIn Live series, Gem Talks, in which we speak with experts within the diamond industry about important topics affecting the sector. This episode is brought to you by GIA, the Gemological Institute of America, protecting consumers and supporting the global gem and jewelry trade since 1931 through research, education, and laboratory services. It's an honor to welcome today's guest, Dr. James Shigley, Distinguished Research Fellow at the GIA in Carlsbad, California. Dr. Shigley helps direct the GIA's research activities on the identification of gemstones. He is one of the best-known names in gemology, having authored more than 180 articles on diamonds and other gemstones. The topic that Dr. Shigley is going to address today is very timely. Right now, everyone in the diamond industry wants to be able to verify the origin of their goods. G7 sanctions on Russian diamonds have gone into effect, requiring importers into the US and other G7 countries to be sure where their stones are from. Can science help determine the origin of diamonds and what challenges are involved? Dr. Shigley is going to begin by speaking about issues around determining diamond origin and the work the GIA has done in origin determination for colored stones. After his address, he will answer some of the questions you submit, so please post your questions in the video chat. Please note that Dr. Shigley is a world expert in the science of diamonds and colored stones, but is not here to speak about diamond sanctions, the G7 certification, or anything like that in the political or commercial fields. So please keep your questions to gemology. We at Rapaport have written lots about the sanctions, so if you have any questions about those, go to rapaport.com, and especially rapaport.com/sanctions. And don't forget to follow Rapaport on LinkedIn. Dr. Shigley, welcome, and it's great to have such an esteemed guest today.
Well, good morning from Southern California. I guess I should go ahead and share that now. Is that right?
Yes, please do.
Well, good morning. I'd like to thank the Rapaport organization for this opportunity. And I'd like to thank those online for joining us today. The title of the presentation is Determining Diamond Origin, Scientific Challenges and Industry Requirements. So we often get asked here at GIA, can we tell where a diamond comes from? And based on current scientific understanding, we know of no way of determining the geographic origin of a diamond from the properties of the diamond. And I'd like to explain in the next few minutes why that's the case. I thought I'd just begin by saying a few words about colored stone origin reporting is to give you kind of a framework for what I was going to be talking about regarding diamonds. So perhaps you know we provide through our laboratory origin reports on some of the important colored stones which are listed here. The origin report is an expert opinion and is based on documenting the properties of the gemstone gathered at the time of the examination. It's based on the experience and expertise of our laboratory staff. And I would say colored stone origin reporting presents a number of challenges for gemological laboratories that offer this service. Because what we're doing is kind of documenting the gemstone properties and then trying to work backwards toward where the stone came from. Just some underlying concepts. The gemological properties of colored stones are at least in part based on the geological environments of their formation, their host rocks. And we're kind of making the assumption that colored stones from different deposits will have different gemological properties. But this is not actually always true. Certain gem deposits cross country boundaries. So gems on both sides of the boundary are going to be very similar. And if there are separate deposits, they may be in very similar host rocks. And any deposit produces a range of qualities, with high quality material always being rare. And of course, some deposits have historically produced gems, colored stones of great value. There are some requirements for origin determination. You have to have criteria. You need to have some reference colored stones of known sources to compare to. You need scientific instrumentation, a data collection analysis procedures, some reference standards if you're doing chemical composition, a database, and of course, a team of experts to make that determination. So when making an origin determination for a colored stone, again, it's based on the properties of the stone at the time we examine it. And they kind of fall into two categories: features we can observe, color, fluorescence, inclusions, and growth structures under the microscope, and so on. And also properties that we can measure, gemological properties, also chemistry, and various types of spectroscopy. And we want to compare the information obtained from the client stone to data on reference gems of the same kind from our database where we know where they're from. So just to kind of summarize the colored stone part of this, you have to identify characteristics that are distinct for gem samples from different origins. And you have to be able to measure these routinely, quickly, economically. You need to have a searchable information database on gems of known origin for comparison. And again, the origin conclusion is inferred. It's an expert opinion. And I just show here on the right-hand side, a couple of years ago, we produced a special issue of our journal, Gems in Gemology, which gave a description in great detail of how we make colored stone origin reports. And I think it's the best resource if you want to learn more of how we do this colored stone origin reporting on ruby and emerald and so on.
Dr. Shigley, Dr. Shigley, can I just stop you a second and ask if the moment everyone can see the two screens, the current screen and the next screen, the current slide and the next slide, do you know if there's a way there of just sharing the current slide so it's a bit larger for everyone? There we go. Perfect. Thank you.
Sorry about that. I'm not an AV technician. So now let's turn to the question, can we tell where diamonds come from? As I said earlier, based on our present understanding, origin determination is not technically possible. Diamonds form in very similar geologic conditions deep in the earth, in contrast to colored stones that form near the Earth's surface in very different host rocks. In addition, diamond values are based on the quality factors, the 4 Cs, and not their geographic origin, because you get high-quality diamonds from almost any deposit. So there's some particular challenges for origin determination for diamonds, which I've listed there, and it's no diagnostic visual features. There's no collections of diamonds for study. In analyzing the trace elements in diamonds as the only possible indication is a challenging process. Well, again, this is probably going to be known information to many of you that, diamonds form deep below the surface of the earth. And there are really now two environments. One, which is about 100 miles down at the base of the solid lithosphere, the solid outer portion of the earth. And over the last few years, based on research here at GIA and elsewhere, we've come to realize that there is another category of diamonds that are forming much deeper, maybe 350 to 400 miles deep below the surface of the earth. And these are the two environments that are producing diamonds, and they are brought to the surface from these depths by eruptions of kimberlite magma. So diamonds were formed millions of years ago near the base of the lithosphere or in the upper mantle. And much, much later, were rapidly brought from different mantle source regions to the Earth's surface through explosive eruptions of kimberlite or lamprite magmas. And I think it's interesting to note that no one has ever witnessed these eruptions because they took place a very long time ago. So what are the challenges for origin determination for diamonds? The first is, in contrast to colored stones, diamonds really don't have any diagnostic visual features of their origin. We've been issuing grading reports since 1955 on millions of polished diamonds, and the vast majority do not exhibit any characteristics that are unique because they occur in diamonds from all geographic origins. And of course, most polished diamonds have higher color and clarity grades, so there are really not many visual features to look at. So in contrast to colored stones, which have features you can see under the microscope, which are rather unique, gem diamonds do not show those type of features. Rough diamonds, I think if you were a sorter at the De Beers CSO years ago and you were taking diamonds from their mines and you were getting a parcel of diamonds coming from a particular mine, I think if you had a lot of expertise, you could say, yes, I know where these diamonds are coming from. But once you mix rough diamonds from different sources, those features, those common features now become much less evident, much less apparent. And of course, the surface features are going to be removed during manufacturing, and then they're of no help for origin determination. The second challenge that kind of confronts the scientific study is that in order to really solve this problem, or at least try to solve it, you need to examine diamonds from all known deposits. By that, I mean primary deposits, which are kimberlite pipes, mines on kimberlite pipes, and secondary deposits, which are where diamonds are found, alluvial diamonds are found along rivers or in sediments. And the important thing is both these deposits contain diamonds that are mixed from multiple sources deep in the earth. So it may be diamonds coming out of a particular kimberlite pipe, but within that pipe, the diamonds don't all originate from the same place deep in the earth. The next question, if you're going to try to assemble this collection for study, is how many diamonds from a source would be representative of a mine? 1, 10, 100, 1,000? And of course, it's even more challenging from an alluvial deposit, a sedimentary alluvial deposit. What's representative of diamonds coming out of a river, where they're coming from multiple sources upstream? If you're examining this selection of rough diamonds, what features need to be studied and how can they be related to polished diamonds? And the only possible indicators that we know of sources are minute quantities of trace elements, which are very difficult and expensive to detect and measure. So the second challenge is there are no such collections that exist of all the mines around the world and sources that are available for scientific study. So trace elements. I have my little illustration there on the upper left, the upper right of the diamond lattice, the black carbon atoms all arrayed. The diamond structure consists of a close packed arrangement of carbon atoms connected by strong covalent bonds. And the impurity elements are randomly incorporated in trace amounts as single atoms during the growth. And the most common impurity element is nitrogen. So the little colored dots, black represents carbon, yellow nitrogen, boron is blue, and this is an example, nickel is green. I've tried to indicate roughly the size of these atoms in a unit called a picometer or PM. You can see nitrogen is a little smaller than a carbon atom, so we can easily replace it in the structure. Boron as well, so you get some, type 2B blue diamonds. But when you want to incorporate a larger atom like nickel, it's twice the size of a carbon atom. It's difficult to incorporate these large atoms in this very tightly packed diamond structure. I wanted to step back just for one slide about chemical analysis.
Yep.
Looking back toward colored stones and just taking an example of blue sapphire, which again comes to us for origin reports. In a corundum, in a sapphire, you've got three categories of components. You have major elements, which in this case, aluminum and oxygen. And if it's a pure corundum, aluminum is about 53% and oxygen is about 47%. You also have minor elements, in this case, titanium and iron, which are the coloring agents. And finally, you have at very low concentrations, trace elements, gallium, chromium, variety of things, which have nothing to do with the corundum or the sapphire or the color of the sapphire. They're just inherited from the host rocks in which the sapphire formed. So these trace elements that are distinctive of a source are distributed unevenly. And so we use an analytical method, and the unit is shown up in the upper right photograph, where you have a laser system on the right and a mass spectrometer, the lighter colored unit on the left. And you're going to analyze a simple, very tiny spots along the girdle surface of the sapphire. And we usually analyze 3 or 4 spots around the periphery of the sapphire to get a more average result. And we're going to compare that to reference standard gems. So that's kind of how we approach chemistry for colored stones, and it would be somewhat similar for diamonds. We're kind of, though, in a world of very low concentrations of elements. So I said that in a sapphire, you have major elements, aluminum, sapphire, and oxygen. And those are typically reported as percents, minor elements, percents, again. But when you get down to trace elements, you get a lot of zeros. So increasingly in the gemological literature, you're going to see minor and trace elements reported in a different unit. It's called parts per million. And I just wanted to kind of show you a comparison of percent numbers versus parts per million numbers. The black vertical arrow kind of shows you the range of minor and trace elements in a colored stone. But the point I'm trying to make here with the red arrow is that trace elements in diamond are at much, much lower concentrations. This is what makes them so challenging to detect. Now you might ask, what is a part per million? What does that mean? So I kind of tried to come up with a little bit of an analogy. Some of you live in New York, I understand. Maybe you've been to a big city. New York, roughly the population is about 8 million. I know that's not quite correct, but for this purpose. So if you want to think of 1 part per million, or the population of New York is 8 people. So it's like we're trying to find 8 people out of 8 million people. Or if you want to think of it as kind of a chemistry, back to the diamond analogy, we're looking for 8 trace element atoms out of 8 million carbon atoms. This is the challenge for trying to chase after trace elements, why it's so difficult. So this is my little diagram again of analyzing trace elements in diamonds. There's a little graphic of what the instrument is doing at the bottom. Again, you have a laser that's focused on the diamond. And in this case, you're going to do that analysis in a sealed box. And then when the analysis is over, then you're going to put acid into the box, and you dissolve everything that has been ablated off the surface of the diamond. And that solution is run through a torch, a high temperature plasma, into the mass spectrometer. And that's how we can do trace element chemistry of diamonds. The problem we're facing is what I tried to illustrate in my little 2 diagrams here. So on the right side, you see the laser kind of flashing, and the red outline shows you the volume of the diamond that you're going to be analyzing. And on the left, you have this green nickel atom that falls within that volume. So during the analysis, you were likely to pick up that nickel atom in the diamond. But if you chose a different spot, because you don't know where the trace elements are, I mean, you can't see them, you can't tell them. But if you have the diagram on the left and you shift over your analysis spot a very small distance and you analyze the again, you don't hit the nickel atom. It doesn't mean it's not there. It just means you didn't detect it. This is the challenge. Low concentrations of trace elements, unevenly distributed, and you don't know where they are. And that's where we're making this determination. Well, when you analyze diamonds for trace elements, there is a pattern. And this is just from some scientific article of diamonds and a whole range of trace elements at, again, low parts per million concentrations. But the pattern of chemistry reflects geologic processes in the mantle. It has nothing to do with the diamonds where they're found today at the surface of the earth. There's a mantle signature, but there's no chemical signature of the crustal sources, the countries, the kimberlite pipes, or the alluvial deposits. The chemistry does not reflect the surface of the earth. It reflects deep in the mantle. So I think origin determination, the prospects of that don't look positive. They look doubtful. It's not possible now, and whereas nor is there any expectation of that in the future. There have been a few scientific studies of origin determination, and they kind of conclude maybe this is possible, but generally, they're too limited in the sample size and too few localities to really solve this issue. And you could spend years analyzing all these diamonds if you could obtain diamonds for study. You could spend years and a lot of money and effort and end up without not results that don't tell you anything. I mean, they tell you about the mantle chemistry, but not about, sources here at the surface. So I think if there are claims that you encounter about origin determination, I think you have to be a little skeptical of those. So what do? We do what's called an origin report, but it really is a matching report. So we examine a rough diamond that comes to us from one of our mine clients, and we document it, and then it goes out and goes through the polishing steps, and we end up having the cut stone submitted to us again. And the question is, can we match the cut stone and the rough diamond? Well, over the past 3 years, we've issued about 30,000 diamond origin reports per year, and that's based on proportion measurements, gemological observations, spectroscopy, fluorescence imaging. And we feel we have about a 90% success rate that we can match a cut stone with a rough crystal that we examined previously. So in contrast to the origin reporting for colored stones, where we're going from the polished stone back to the origin, in this case, we're going from the rough diamond of known origin to a polished diamond of known origin. So it's much more similar to a chain of custody. This is what I think is possible today. This is what we do. And I don't think there's any way of telling just from studying a polished diamond where it comes from. I just wanted to finish just with a couple of comments about laboratory-grown diamonds, which, as you know, are in vast numbers out in the trade today. I think this is the key difference between natural and synthetic diamonds. Natural diamonds formed long ago, deep in the earth. Synthetic diamonds formed a short time ago, very recently, in the laboratory. That's what we call them today, laboratory grown, but I think it's really a factory. I think we should be using a little better core trick terminology. But I think the key difference, diamonds may grow quickly in the earth, but they're down there in the earth for millions of years under these high temperature and pressure conditions. And a lot can happen to the diamond during that time. So while a synthetic diamond reproduces the chemistry and the properties, it is impossible to recreate that long geologic history, the evidence of that history that's in a natural diamond. And that's always going to be the case. And we've been studying lab-grown diamonds for more than 40 years. I guess there may be 30 articles in our journal. We published kind of 2 reviews several years ago. If you wanted to see these, they're available on our website. But it kind of summarizes all the observations on the 2 categories, CVD and HPHD grown synthetic diamonds. But I think the good news of all these studies is that they can be positively identified in our laboratory. There are a lot of diamond testers being sold, and this is ours. It's the ID100. It's based on fluorescence spectroscopy, but it is very effective for, diamonds, rough, polished, all sizes, loose or mounted, kind of colorless, near colorless, faint yellow, light yellow, with a quick analysis time. And it's a very simple way of giving you a tool that you can use to check diamonds, whether they're natural or synthetic. And we issue various types of reports on laboratory-grown diamonds, and we inscribe them when they come through us. But I think the good news is that while they're abundant, they can be identified, but I think they're only going to continue to be present in the jewelry trade. So with that, I hope that I didn't run too much time over, but I thank you for your attention. I'd be glad to answer any of your questions.
No, that was perfect, Dr. Shigley, and thanks for enlightening us on all of that. We are going to take some questions now. We will continue to accept questions throughout this Q&A session, so everyone please continue to post in the video chat. And as I mentioned before, please submit questions on the science of diamond origin. Dr. Shigley is not here to give his views on customs rules or the role of Antwerp or anything like that. We do have a few questions that are coming already. First one is, other than trace elements in diamonds, what identifying features can help you determine its origin? For example, do diamonds from certain regions like Argyle pinks give off different fluorescence when looked at under ultraviolet light?
Well, I would say Argyle pink diamonds are kind of an anomaly. They're very unusual because of their formation conditions. And of course, the Argyle mine is no longer in operation. But I think in general, for most diamonds, the challenge is we just don't know if these features are going to show up elsewhere, because no one has ever had a diamonds really such a wide variety of sources to study. I'm just saying that 55 years or 60 years or whatever it's been of diamond grading reports, there just haven't been distinctive properties that we've recognized from diamonds from different sources, except for, again, Argyle pink diamonds, which are really rather unusual. And of course, colored diamonds are so rare that they're really not that, they're high value, but they're not that abundant in the marketplace.
All right. On that issue, that there have been a few, this is my question, but that there have been 1 or 2 organizations that have claimed that they are able, or at least are working on being able to identify the origin of a diamond from trace elements. Are you able just to enlighten us on what, are there just different assumptions going on? Is there 2 different approaches in the science to this, or why would there be, given what you've said, why would there be organizations that are claiming that it is possible?
Well, there are different conclusions for colored stone origin reports from different organizations. So again, I think we approach this in different ways. But I think you have to actually ask the people who are saying this can be done, how did you do it? What samples did you study? How many diamonds did you study? I'm saying the studies that we've seen, they've been too limited in samples, localities, numbers of samples. And we're just a little skeptical because they oftentimes don't really want to tell us what they're doing. And I think that's not the right science. This is an important question. I think I would never say that this will never be possible. But I'm saying so far, we have seen no evidence that this can be done on random diamonds from many, many sources. Maybe it will in the future, but so far we not seen such a study.
I see. We have a request to see our faces larger. Dr. Shigley, would you be able to stop sharing the presentation, please? Great. Thank you very much.
Faces larger. Okay.
Yeah. So I've got a couple of quite technical questions here. I'm going to read them out. I'm also Dr. Shigley. We've got a little chat here. I'm just going to send it to you in writing as well, as well as reading it out. Can isotopic analysis, by looking at the ratios of different isotopes of elements within a diamond, help to identify its geographical origin, as isotopic signatures can vary depending on geographical processes and conditions in different diamond-producing regions?
Well, there's certainly different isotopes of carbon. One can detect those. I don't know how destructive that kind of analysis is if you have to, destroy part of the diamond to make that determination. But again, if the signature is of deep in the metal, it's not, this country or this country. There may be variations, but no one has demonstrated that diamonds from this place always have this kind of isotopic signature. Maybe it's possible. I'm just saying no one has done that. And without a real collection that's representative of all these sources around the world, I think it's kind of hard to make the claim that this is a solution.
Okay, thank you. Another question that came in is, how can you be sure that natural diamonds have been formed in a very long period?
I'm not certain they were formed in a very long period. I think they may form quite quickly if you got the right conditions of carbon source and temperature and pressure in the earth. But the formation time is not really the important idea. They may form quickly, but they're sitting down there at high temperatures and pressures for millions of years. That's the difference between quick growth in the laboratory versus quick growth in the earth, but followed by very long residence time. And during that residence time, you can get growth of diamond, dissolution of diamond, regrowth of diamond. So you oftentimes see a very complex fluorescence pattern, which reveals this growth structure. You have diffusion of nitrogen and other elements into the diamond, which requires a long time because of the diamond structure. You can have defects in the diamond that are causing the color that either form or modified or destroyed. I think a lot of the colorless diamonds, this is kind of my opinion, so it may be totally wrong. The type 1A tape diamonds, I think initially were yellow in color. They were 1B diamonds because diamond enters the structure as single atoms. That's a yellow 1B diamond. So I think a lot of them started as yellow colored diamonds, and over geologic time, the nitrogen atoms migrated through the structure and aggregated, and it went from a 1B to a 1A diamond and changed from yellow to colorless. So a lot can happen over millions of years that can't happen in a few weeks in a lab environment.
Okay. We've got a technical question here about equipment. I'm not going to pretend I actually know. I completely understand this question. I'm going to read it out anyway. Is one of the challenges in the LAICP-MS having a high spatial resolution? I'm going to put that in the chat we've got as well.
Yes, I think, spatial resolution is, how kind of small an area, but the challenge is that we don't know where the trace elements are initially beforehand. We can't see them. And so I guess the next question is, well, how many analysis spots are we going to burn on your diamond to determine its origin? These are all questions that are valid questions for a scientific study. Without representative diamonds, you're going to spend a lot of money, years of work chasing after these things, and it may not end up with a positive result for the question that we're interested in today.
Dr. Shigley, would you mind just explaining for those of us who don't know what's the significance of high spatial resolution?
I think it's kind of analysis spot size, or how small an area can you really analyze? But if we knew where the trace elements were, we'd probably have better luck at finding them. But we can't tell where they are initially. In a colored stone, they're much more, the trace elements are more abundant. Oftentimes, they're kind of aligned along, for example, color zoning in a sapphire or ruby, or related to the crystal shape. But when the diamonds are deep on the earth, they're sitting down there for a very long time, and how these trace elements enter the diamond and where they are now, it's just a challenge. We just don't know. And I'm just saying, so far, these chemical signatures are not telling us about crustal locations. It's metal environment.
Okay, thank you. We've got some praise for your presentation, and also, what color diamond is the hardest to determine origin for?
Well, I think they're all difficult because of the reasons I tried to summarize. I mean, colored diamonds are kind of a different category. They're much rarer. There's certain mines that have been known to produce things. But again, if you're sitting here taking diamonds in from the trade polished diamonds, you can say, well, this diamond could not have come from this place. That place doesn't produce good diamonds, but you can't make that assumption. You can't assume you're going to just ignore certain places because there is no history of that. We kind of have to do this a little more. Let's kind of focus on the evidence. And I'm just saying, for diamonds, there's not a lot of evidence, and the evidence that's there is difficult to obtain, and it is not telling you anything about country A or country B.
All right. So on that issue, we have a question about, do you think there would be different trace elements in colored diamonds from the same region, but different mines, such as yellow diamonds from Akati or Diavik in Canada's Northwest Territories?
Well, there could be, but we don't know. And again, I know years ago I had a chance to go up to the Royal Canadian Mounted Police Laboratory in Ottawa because they were trying to fingerprint Canadian diamonds as opposed to diamonds coming in across the open borders of Canada to get what I guess you would say the Canada mark. And they couldn't solve the problem, just like we're having trouble solving the problem. The trace elements are such low concentrations. We just don't have a database. If there's a book that say, diamonds from this place have this characteristics, but there's no book. We have to kind of create the book or the database, you might say. And I don't think that database exists. De Beers mines, they probably have some idea, but that's not reflecting everybody. That's just their mines. So I'm not saying no data exists. I'm just saying there's no published scientific study of a large number of diamonds, very large number from a very large number of localities that demonstrate that origin determination is possible. So far, anyway.
All right. Thank you. Question here. Do you think either ICP-MS or LIBS methods can determine geographical locations if a database of those areas are available? Now, I think before we hear an answer, I think many of us probably need to understand the question. Dr. Shigley, are you able to just explain what some of those terms are before answering?
What we're talking about here in the talk today was laser ablation, LAICP-MS, laser ablation mass spectrometry. LIBS is a different technique. It's an analytical technique, which you shine a laser at a gemstone, and it causes the gemstone to emit light. And in that light, there are signatures of the various elements. But I'm not quite certain how one quantifies from that light signal the concentrations of the elements. Are you analyzing the right place? Again, we don't know what the right place is. And there's just no data. No one in the world has access to diamonds from all these places to conduct a study or the funding. It might take, a couple of years of very expensive burn up diamonds, that type of research. We just don't have the data yet. Maybe in the future there will be some data, but I think that as what we know today, we cannot make this determination by any analytical technique.
Right. So just focusing on the diamond origin report, which obviously works by matching the polish to rough wood known origin. Could you just go into a bit more detail about how that works and how the science works and what exactly it is that you look at in the rough that you're able to match with the polished?
Well, we're looking at visual features, clarity features, inclusions, and whether they would be retained or not in a cut stone. We're looking at fluorescence, colors, patterns, distributions, fluorescence reactions. We can record fluorescence spectra. So we have a very good idea of the fluorescence spectra. We can also type the diamond, type 1, type 2 by infrared spectra. We can also record visible spectra, which is a way of looking at the optical defects at the atomic level, which produce, for example, color or spectral features. So there's a lot of evidence that we gather, just the proportions of the rough piece. We're looking for everything we can think of course, to document the rough stone, and we produce a data set on that rough stone. It goes back to the mine. It goes through the process of manufacturing. It comes back. And then the question is, can we do the same characterization on the cut stone? And can we match the features? We seem to have a pretty good track record. It's not always possible for whatever reason. But I think that there's a variety of features that we can look at, visual features, spectroscopy features. We're not analyzing trace elements in diamond. If we don't actually have the technology to do that here. We have a colored stone analysis, but not diamond, because of the trace elements are so much lower concentrations. And it might be, I don't know, $1 million piece of equipment. So, but it's just matching all the features that we can visually see, and we can record by spectroscopy, which is non-destructive, and try to match. And that combination is a pretty good fingerprint of that when we see it in the cut stone.
And you said that it was a 90% success rate.
Yeah, I think that's pretty close.
Does that mean there are false positives, false negatives? How does that actually? What's the actual implication?
I would say if we're issuing this is a match, we are pretty convinced. I mean, we're not issuing that just based on we think there is direct evidence that of the fluorescence pattern and so on in the cut stone that matches the original. And there are times when we can't issue a report because we don't get enough of a match. Right. We don't issue the report then.
So that 10% would be cases where you're just not confident to say that it's
yes. That it's there's no features that are really, we just can't prove to our satisfaction that it's the same.
Right. Is there a way of, this is one of my questions, is there are you able to identify, even if you can't identify where it's from, are you able to identify whether a diamond is from a kimberlite mine versus alluvial or artisanal? Based on chemical
No, because ultimately, whether they're from a kimberlite pipe or they're from a kimberlite pipe and then it goes through the river, it's the same. And I have to say one other thought. It is interesting to me that we're getting questions now, can you tell where your lab-grown diamond is grown? Yet, we can't. Yes, the growers, or you're growing either in a CVD is just in a reactor where there's nothing except gas in the reactor. And the HCHT process, you're growing from a metal solvent, and maybe different manufacturers have their own metal alloy that they use. but we can't tell where synthetic diamonds are growing either.
Okay, interesting. I have a very interesting question here. Do you think there could be structural changes to diamonds that will be mined in the future due to climate change?
I don't know of any features due to climate change. I mean, the diamonds are so, they're a couple billion years old, perhaps. They didn't form, in modern. I mean, all the diamonds that are mined, came up in Kimberlite eruptions millions of years ago. So there's nothing, modern going on here. It's very old diamonds versus, very young synthetic diamonds.
Right. And is there, just focusing on synthetic diamonds, I'm interested also to know what your views on the future applications of synthetic diamond. I don't know if this is a field that you feel able and confident to comment on, but what is the potential for synthetic diamonds to be used for a wider variety and a more valuable variety of technical applications in the future?
Is a little outside my narrow field of knowledge, but diamonds in general have so many important physical, chemical properties. They are so valuable for many, many applications, both kind of, grinding, grooves in the streets and, computer chips and everything in between. That's what's driving the research. I mean, the synthetic diamonds directed toward the jewelry trade is an interesting application, but I don't think that's the big ticket. I just think this is what's going to continue to drive the production of synthetic diamonds for so many applications which we haven't even thought of today. I think that's only going to continue.
Right. And moving back to colored gemstones, I apologize if you mentioned this already, but if you were to comparing different colored gemstones, which of those are the easiest to, in terms of tracing the geographical source?
Well, I think colored gemstone origin reporting, started in the 1940s with Edward Gubelin in Europe, whose family company was selling colored stones, and their clients were asking, where do these come from? But in the 1940s, they were, issuing, sapphire origin reports or ruby origin reports and so on. There were just a lot fewer localities to deal with. And that was mainly based in his day on inclusions, which he was the pioneer of looking at inclusions in the stones. The challenge today for my friends here in the lab is the fact that, you get very similar looking material from very different places, sapphires that are very similar, attractive sapphires from very different countries. And that's because their deposit is the same rock, coast rocks. But I think the challenge is they're getting more and more localities around the world for colored stone production. And again, the comment I made about diamonds, if you get a sapphire, high value sapphire or ruby, it comes in, you just can't say, well, it never could have come from this place. That place doesn't produce high quality material. You cannot make that assumption in a laboratory setting when you're doing origin reports. So again, we're trying to kind of make that determination on as many different criteria as possible. Again, if you look at that special issue in 2019 winter issue, that is the best detailed explanation of colored stone origin reporting, I think, that's been published by any organization. And again, answers a lot of questions. I think some challenges are probably metamorphic blue sapphires where they come out of a marble as opposed to igneous blue sapphires out of a basalt. I think metamorphic sapphires, I'm not a real gemologist in the opinion of my colleagues here, but I think there are some challenges, and those are going to continue and makes it quite difficult. So we have to try to kind of find additional means of identification So we're exploring, different means of analyzing data, not just in a two-dimensional graph, but maybe artificial intelligence or, advanced statistical methods for chasing after trace element patterns, because they are important for colored stones.
Do those advances have any impact on where we stand in terms of tracking diamonds, or are we back to the same issue?
We're still at the same problem. We still don't have a collection to test out any ideas, and testing out is going to be a lot of work and a lot of expense. And you'll definitely get results, but the results may not solve the question that we're interested in. It'll tell you a lot about chemistry in the metal, but not about chemistry in different kimberlite pipes.
Right. That was my next question about the lack of a large collection. I imagine that the first barrier here is expense, but would there be a way of creating a collection of diamonds of known origin at lower expense, say using very, very low quality material?
Well, you certainly could start there, and then you have the question of those results, can you relate those to high quality material? I think at any kimberlite pipe that they're going to mine, they have to kind of make a statistical evaluation of the qualities of the diamonds in that pipe before the mining starts. So I think there are probably statistical methods that can kind of be used to say, well, if we're going to sample this kimberlite pipe, how many diamonds do we need to study? I think that probably is a mathematical solution to that. But then just physically assembling them, and that's a lot of diamonds potentially. And the fact that we might have to burn some of them up in their high value might kind of be a little bit difficult for clients to think we're burning up their diamonds. But I'm just saying, I think the real problem is not the kimberlite pipes. I guess there may be about 30 mines in the world today, all the countries, 30 mines, 40 mines, whatever, that small number. It's the alluvial deposits. If you're standing by the river in West Africa and you find one diamond this today and one diamond a month from now, what's representative is both the kimberlite in the river, I think, are sampling various sources. In South Africa, you know that the diamonds are coming down the Orange River into the Atlantic Ocean. They go north and end up on the beach in Namibia. But they're coming from a number of kimberlite pipes in South Africa. So you're sampling a lot of different locations in this one alluvial deposit, and all you have is a diamond. And you don't know where it's come from. I think it's the same with the kimberlites. You're sampling different regions of the mantle. It's kind of like an elevator. You get on the elevator at various levels, and you come up to the surface. But it's the alluvial deposits, what's representative there. I think it'd be much harder to kind of solve.
Right. With another question, the diamonds originating from different areas have varying octahedral patterns.
Well, again, I think the rough crystals have kind of a characteristic look from different mines. That's what the De Beers sorters told me when I went to the CSO years ago. Here's all these diamonds from this mine. They kind of have similar looks. But again, those surface features are all cut away, when the manufacturing, and they're gone. And of course, I think De Beers in those days was deliberately mixing diamonds from multiple sources, so their manufacturing clients felt they were getting a fair selection. But once you remove all those surface features, they're gone from any, evidence for an origin.
I see. Another question. Let's say this question is out of this world. Is there any evidence of originally extraterrestrial diamonds?
Well, I'd say probably yes, because carbon is a common element. in the universe. And anytime you get the right conditions, you can make diamond. And I think there's probably a lot of diamonds down in the earth. They just didn't get tapped by a kimberlite eruption to come to the surface. But I think in outer space, a lot of the diamonds might be micro diamonds, very tiny things. And I've heard that, some planets might be a lot more diamond. But that's we're not there yet. Carbon is a common element. So whenever you get the right conditions, diamond will form.
Right. Okay, great. Well, I think we're gonna leave it there. A big thank you to Dr. James Shigley of the GIA, firstly for giving his enlightening presentation and also for answering our questions. I think we're all a lot more. At least I'm a lot more educated on this topic than we were.
Well, I hope
before.
this was helpful. If you have any questions, certainly can contact me at any time in the future. This is J. Shigley at GIA.edu if you want to email me. But thank you so much. And hope to see you again sometime.
Well, thanks to everyone for watching and for submitting your questions. This episode of Gem Talks was brought to you by GIA. And don't forget to follow Rapaport on LinkedIn. Goodbye, everyone. And thank you, Dr. Shigley.